Hi, I'm Jiyoung-an.
I'm Yoon Cho.
Our project is about 3D object pose detection. Before we start, we'd like to clarify that we are not focused on creating a novel method. Rather, our aim was to survey two branches of existing methods and reproduce the result based on our understandings. In this project, we would like to tackle 3D object pose detection. This is a critical component of perception with applications such as autonomous driving to localize other agents in roads or mobile manipulation to assess the target object pose prior to planning labs. With growing demands in autonomous driving and robotics, 3D object pose detection has been more important than ever in recent time.
Despite its importance, monocular 3D object detection is an inherently ill-posed problem. Purely geometric reasoning cannot recover this information without semantic priors in a single frame. Therefore, most methods use spatial hints such as depth or otherwise impose geometric constraints. While simple approaches such as IncenterNet directly regress to 3D bounding box parameters, others such as CADDN explicitly incorporate monocular depth estimation cues in order to recover spatial information about the target objects. 3D deep box incorporates a two-stage pipeline in which the 2D projected bounding box constraints are exploited for lifting to the 3D detection. And finally, methods such as mobile pose detect object key points and incorporate classical geometric algorithms such as PNP or perspective endpoint in order to compute object pose from the key point representations. Recently, methods incorporating temporal information has begun to emerge. However, single frame baselines still currently remain at the top with very strong performance. As we have yet to explore temporal reasoning in sufficient depth, methods without temporal context will be the focus of our discussion for the remainder. Previously, the only datasets available for this task were either small-scale or restricted to specific environments such as urban roads, rather than common household items. Recently, the Google Objectron dataset was released to mitigate such issues. This is a 3D object pose and bounding box dataset annotated on video sequences with over 15K annotated video clips and 4 million annotated images amongst common objects such as bikes, books, chairs, shoes, etc. It boasts a rich set of features including object and camera pose, point cloud, surface planes, and of course the bounding cuboids. It is one of the first large-scale datasets to have been released in this domain, which is ideal for our purpose. With this problem setting established, we will now discuss our model architecture. Specifically, we'll discuss two different approaches for single-frame 3D object detection in terms of keypoint-based and bounding box-based representations. Our keypoint-based architecture is based on 2D detection of representative points, and therefore we need to exploit specific geometric properties in order to convert it into 3D. In order to achieve this, our pipeline is factorized largely into 5 steps. First, we compute features via the ResNet backbone with FPN, which are then processed into heat map-based keypoint representations. These keypoint heat maps are then extracted through spatial non-max suppression and top K pruning, followed by association with the respective objects and offset. Lastly, the 2D keypoint set is lifted into the 3D object pose via the perspective endpoint or PNP algorithm. That was the idea at least, which unfortunately did not go as planned. We'd like to share our failures on the keypoint-based architecture. While fine on toy datasets upon training and evaluating on the real data, we have encountered a number of architectural issues. Firstly, we have noticed training instabilities with displacement math encoded keypoints per the reference implementation in mobile pose. Hence, we have altered the layers to perform coordinate regression based on Gaussian heat maps instead. On the top left, we share the results from a trained network, which appears to identify the correct object centroids and the vertices, albeit quite hazy. Note that this is already a rather easy example with well-defined corners and rich textures on the object. Indeed, we continue to have difficulties with the keypoint-based models. On the bottom, we share two of the insights that we have learned through this process. On the left, you see a sample on the representational degeneracy for symmetric objects, which we have later realized is a well-known issue. Indeed, in DRNet, the authors state that methods based on keypoints cannot resolve symmetric object pose estimations and occluded seams. Further, we have noticed a tendency for the keypoint network to find object corners for bitexture rather than spatial vertices. For these reasons, we have focused our energy more on bounding box-based models afterwards.
We designed architecture for 3D bounding box regression as shown in figure. This model projects 2D box to 3D. Since we do not focus on 2D object detection, we assume that the class and the 2D bounding box of objects can be found through the 2D object detector and supply the ground truth input at this stage. Based on the 2D boxes, we crop the image of the corresponding region and resize it to the fixed site. Each of these cropped images is fed into the backbone network to extract feature maps. These feature maps are processed through a set of fully connected layers to predict the object orientation and dimensions. Finally, a translation is calculated using constraints of 2D box. 2D box consists of 4 vertices. On the other hand, 3D box is represented by 9 constraints: translation, orientation, and dimensions. 2D box provides 4 constraints for 3D box. However, this is insufficient to meet all the constraints for 3D. Therefore, the network must predict additional geometric characteristics of 3D box. To this end, we employ an additional module that predicts dimensions and orientations. Using upper equation, the translation can be inferred from the constraints of 2D box and regressed orientation and dimensions. To solve this equation, we transfer the form of linear equation about translation, shown below, and use the single value decomposition. This yields translation that meets to the least scale solution. In order to find the solution through optimization, the set of matching between the vertices of 2D and 3D must be needed. This determines which constraints are activated in the optimization, as shown in the right figure. Since we don't know the matching, the number of possible cases is 8 to the 4th power. We found the least scale solution for all these combinations and then adopt the smallest error solution. However, to speed up our pipeline, the number of cases can be reduced by using geometric properties.
Now we'll discuss our models of evaluation results on the benchmark against a test set from the Objectron dataset. In the slide, you see a set of samples from the cup class from the Objectron test suite. And what you see is that occasionally the model does perform quite well on the detection of the object poses on the cups. However, there are a set of failure cases. So the objective here is not to cherry pick the best examples, but rather to show the model outputs from our current model truthfully. You can also see some examples from other classes, such as laptops, and likewise, we see some successful detections and some misalignments along the way. And we can validate this with the quantitative results as well. So in the table shown, summarizes the evaluation results against the Objectron benchmark, compared against the 2 baselines with mobile pose and efficient at light with key point regressors. In the table, we report 3 metrics of AP, or average precision, evaluated at 2 different thresholds of 3D bounding box IOU, or inner external reunion, and AE, that is azimuthal error, and additionally provides scores on the mean pixel error in 2D as well. Overall, our model does not outperform the strong baselines. In spite of this, we're hopeful that further work in the model architecture and training would lead us closer to the current baselines. In order for us to improve our architecture, the current remaining works on the plate are as follows. In terms of the key point network, we would be curious to experiment with different key point definitions from the current cuboid vertices in order to better reflect the inner structure of the respective objects. Further, in terms of the bounded box networks, we would like to experiment with different orientation parameterizations, knowing that they influence the output quite significantly. We would like to see the joint inference on class, whether that would allow for a pathway for semantic information to flow into scale predictions, or alternatively regress to the residual from the categorical mean instead of independently predicting scale instance to instance. While not high priority at the moment, we would also like to reduce the number of permutations on the possible set of bounding box vertex assignments for the 2D least squares constraints. Thus, we have presented the problem of 3D object pose detection from a single image. We have explored 2 potential approaches from literature, bounding box-based regression and key point detection. Both methods are inspired from 2D object detection and apply geometric priors in order to lift the detections from the projective image plane to Euclidean coordinates. We have implemented both approaches and evaluated our results in the Objectron dataset and compared against the strong baselines. Whereas we are still in the process of improving our architecture at the current stage, the network demonstrates promising but not groundbreaking results. Thank you for listening. That is the end of the presentation.